Hello, today we're going to talk about how free energy relates to equilibrium. So let's review equilibrium really quick. If we have our reactants and our products, we know that our equilibrium constant is the ratio of the products to reactants. So if I have a situation where K is greater than 1, then I know that the products are favored. In this scenario, where the products are favored, delta G, standard delta G, is going to be less than 0. It's going to be negative or thermodynamically favorable in the forward reaction. So negative for the forward reaction. If I have a situation where K is less than 1, I know that the reactants are favored. In this scenario, my standard delta G is greater than 0. So it has a positive value for delta G, and that means it is not thermodynamically favorable in the forward direction. We're always thinking about the forward direction. Then, if we have where K is exactly equal to 1, when that happens, delta G is equal to 0. And of course, this is standard conditions. And so we say that this is at equilibrium. Now, you can have reaction systems where the K value is not equal to 1, but you are at equilibrium. However, when we're talking about thermodynamic standard conditions, equilibrium will happen when K is equal to 1. So this is kind of like a special case scenario. But when you're at equilibrium, your reactants and products are equally favored. The rates of the forward and reverse reactions are equal. And in this situation, there's no net change in free energy, so your delta G is 0. So there's an equation that we use to convert between delta G and K, and it's delta G equals negative RT ln K. So if you know the equilibrium constant, you would plug that in, take the natural log, and multiply by the temperature in Kelvin and by R. Now be careful, because we're doing thermodynamics, we need to use the value of R that incorporates joules. So the value is 8.314, and its units are joules per mole Kelvin. Remember, gas laws, we typically use 0.0821, but that one will give you ATM in the units, so that's your clue. Like, don't use that one. For thermodynamics, you want to use the one with joules in it. So you would just take the natural log of K, multiply by the temperature and the constant there, and you'll get your value for delta G. If you were to rewrite this equation, let's say you have delta G and you're trying to find K, when you rearrange the equation, you would do delta G divided by negative RT equals ln K, and then so it would be E to the negative delta G over RT equals K. So that's how you would rearrange that if you needed to. So here's an example reaction, and then gave you the equilibrium constant 1.40 times 10 to the 6th. Calculate the value for delta G. So delta G equals negative RT ln K. And let's plug in our values. It's negative, so 8.314 for R, 298 for our temperature in Kelvin, and then ln K. Take the natural log of K first, then multiply, and you get that the delta G is equal to negative 35100. Now, because our value of R is in joules, whatever answer you get is also in joules, joules per mole, really. So most of the time you will be asked then to change that into kilojoules, so it will be negative 35.1 kilojoules per mole. So here's another example. We have our weak acid dissolving in water to form the conjugate base and hydronium. So it has a Ka value because it's a weak acid in water. But because we know the equilibrium constant, we can find delta G equals negative RT ln K. Oops. And then so you would do negative 8.314 times the temperature in Kelvin is 298. Ln, and our equilibrium constant is 5.5 times 10 to the negative 3. And so our delta G, when we solve that, is 12,900 joules per mole, or 12.9 kilojoules per mole. Now notice K is less than 1, so delta G is positive, which means it is not thermodynamically favorable at that temperature.